In this video, I want to have a look at the relationship between the roots and coefficients of polynomial equations. So to start with, we're going to look at quadratics. So we know that a quadratic, the general form, is ax squared plus bx plus c equals 0. Now, if that quadratic has two roots, so we're going to call them alpha and beta, we know that we can write the quadratic with roots alpha and beta as x minus alpha, x minus beta equals 0. So we're going to rearrange both of these equations to get them in the same form so that we can compare coefficients. So if we rearrange this into a monic quadratic, we're going to have to divide every term by a. So we're going to have x squared plus b over ax plus c over a equals 0. If we rearrange this one so that it's a monic quadratic, the first thing we're going to do is expand. So we'll have x squared minus beta x minus alpha x plus alpha beta equals 0. And then we're just going to collect these two like terms. We're going to factorize out the x. So we're going to have x squared minus, and I'm going to rewrite my alpha and beta the other way around, so alpha plus beta. Now that becomes a plus because we've pulled the negative out the front, and we've also pulled out that common factor of an x. And then we've got our alpha beta on the end. So now we can compare these two equations to come up with a relationship between the coefficients, so our a, b, and c, and our roots, our alpha, beta. So our x squareds are both just have a coefficient of 1, so that's fine. Our x terms, this one has a coefficient of b over a, and this one has a coefficient of minus alpha plus beta. So that means that minus alpha plus beta has to be equal to b over a. So we've taken this coefficient here and equated it to this one. Now we usually rewrite that just to alpha plus beta equals minus b over a. So we've just brought that minus over the other side instead. So that means that the sum of our roots of our quadratic equation is equal to minus b over a. We can also do it with the constant terms. So that means our alpha beta, so our two roots multiplied together, or the product of our roots, is equal to c over a. So alpha beta equals c over a. So that's with quadratics, but these similar relationships between roots and coefficients will work for any polynomial. So let's have a look now at deriving it for cubics. We just did quadratics. So a cubic would be ax cubed plus bx squared plus cx plus d is equal to 0. Now if we say that it has roots of alpha, beta, and gamma, then we would write it as as x minus alpha, x minus beta, and x minus gamma equals 0. So again, we're going to rewrite this as a monic cubic. So we're going to have x cubed plus b over a x squared plus c over a x plus d over a is equal to 0. And we're going to expand this out. So I'm going to expand out my two second brackets first. So leave my first one as it is. And then we'd have x squared minus gamma x minus beta x plus beta gamma equals 0. And then expand out again. So we'll have x cubed minus gamma x squared minus beta x squared plus beta gamma x. And I'm going to run out of room, so I'm going to start down here. So we'd have minus alpha x squared plus alpha gamma x plus, because we're going minus times a minus, so plus alpha beta x minus alpha beta gamma equals 0. So this one's looking a lot messier, but it's still going to work. So we've just got the one x cubed term, so that's fine out the front here. Then we're going to collect our x squared terms. So we've got this one, and this one. So we're going to put out our negative. I'm going to rewrite them, in alphabetical order, or Greek alphabetical order, so alpha, beta, then gamma. So alpha plus beta plus gamma, because we've pulled all the negatives out the front, and that's our x squared. Then our x's, so we've got this term here, this one here, and this one here. So we've got plus. Now we've got an alpha beta here. We've got an alpha gamma. And we've also got a beta gamma. And that's x, and I've run out of room. But our last one is just our constant term, so minus alpha beta gamma equals 0. All right, so now even though it's on 2 lines, we can still compare. So again, they're both monic, so they both have a leading coefficient just of 1, so that's fine. But we can equate coefficients of x squared. So we would have alpha plus beta plus gamma equals minus b over a. And again, this has become a minus because we had a minus here. So instead of putting it over this side of the equation, I've divided through and put it with our b over a instead. Then if we have a look at our coefficient of x, we've got alpha beta plus alpha gamma plus beta gamma is equal to the coefficient of x here, which is c over a. And then we look at our constant term, so we've got minus alpha beta gamma is equal to d over a. And I'm going to do the same thing we did up here. I'm going to take the minus off this side, so divide through by -1, and put it over this side instead. So we start referring to these as the sum of the roots 1 at a time, the sum of the roots 2 at a time, and the sum of the roots 3 at a time. All right, next I want to have a look at quartic, so polynomials of degree 4. So a quartic equation would have ax to the power of 4 plus bx cubed plus cx squared plus dx plus e equals 0. And it would have 4 roots, so we would call them alpha, beta, gamma, and delta. Now I'm not going to go through the whole process of working these out. It's just the same process as our quadratics and our cubics. But what we do end up with is this. Right, so we've got the sum of the roots 1 at a time, so each individual root added together would still give us that minus b over a. The sum of the roots 2 at a time, so that's all the possible combinations of our different roots, so all the possible pairings added together, would give us c over a. The sum of the roots 3 at a time, so all the different combinations of 3 roots added together would give us minus d over a. And the sum of the roots 4 at a time, would give us e over a. So when you start looking at these, you can see the pattern that's emerging, and the pattern would continue for polynomials of degree 5, 6, 7, 8, forever. All right, let's have a look at a couple of examples. So our first question says, if alpha, beta, and gamma are the roots of the equation 2x cubed plus 2x squared plus 3x plus 4 equals 0, we want to find the value of the sum of the roots 2 at a time, and the product of the roots. So to do this, we're just going to write that a equals 2, b equals 2, c equals 3, and d equals 4. So that's just reading our numbers straight off here. Now a, we know that alpha plus beta plus gamma, that has to be equal to minus b over a. So then we've got our numbers over here, so we would have minus 2 over 2, which would just give us minus 1. All right, for part B, we've got alpha beta plus alpha gamma plus beta gamma equals, so that's going to be c over a. And looking at our numbers, we're going to have 3 over 2. And our last one for C, alpha beta gamma would be equal to minus d over a, which would give us minus 4 over 2, which would just be equal to minus 2. Our second question says if alpha and beta are the roots of the equation 2x squared plus 4x minus 5 equals 0, we want to find alpha squared plus beta squared and 1 over alpha plus 1 over beta. So just to start off, we know that our a is 2, our b is 4, and our c is minus 5. The other thing we do know is that alpha plus beta would be equal to that minus b over a, so minus 4 over 2, which is minus 2. And alpha beta, the product of the roots, would be c over a, so minus 5 over 2. Now this isn't what it's asked us for, but we're going to have to use those results to get these. So for part A, alpha squared plus beta squared, we can't do that straight away. But what we can do is we know that alpha plus beta all squared is equal to alpha squared plus 2 alpha beta plus beta squared if we were to expand it out. So that's giving us our alpha squared plus beta squared, but it's also giving us this extra term in the middle. So what we're going to do is we're going to subtract that 2 alpha beta from both sides. So we're going to have alpha plus beta squared minus 2 alpha beta will give us our alpha squared plus beta squared. So that means alpha squared plus beta squared is going to be equal to alpha plus beta all squared. So we know from up here that alpha plus beta is minus 2. So we're going to have minus 2 squared minus 2 times alpha beta. And alpha beta was minus 5 over 2. Right, so minus 2 squared is 4, and minus 2 times minus 5 over 2 is plus 5. So that will give us 9. Right, for B, we want 1 over alpha plus 1 over beta. Now again, we can't do that straight up, so we're going to have to manipulate it. So let's make it have a common denominator. So our common denominator is going to have to be alpha beta. So to get this one to have a denominator of alpha beta, we would have had to multiply top and bottom by beta. And to get this one to have a denominator of alpha beta, we would have had to multiply numerator and denominator by alpha. So now we've got beta plus alpha, which is the same as alpha plus beta, over alpha beta. So we're going to have minus 2 over minus 5 over 2, which is the same as minus 2 times minus 2 over 5. So we've multiplied by the reciprocal instead, which will give us 4 over 5. Our third example asks us to find the quadratic equation whose roots are the squares of the roots of 2x squared plus 3x plus 5 equals 0. So what that means is if we're calling the roots of this equation alpha and beta, then our new equation is going to have roots alpha squared and beta squared. So if we've got roots of alpha and beta, we know that our equation can be written as x squared minus alpha plus beta x plus alpha beta equals 0. And our new equation would be written as x squared minus alpha squared plus beta squared x plus alpha squared beta squared equals 0. So we're going to start looking at this one and leave this one for a minute. And we're going to find alpha plus beta and alpha beta. So alpha plus beta, the sum of our roots, would be equal to minus b over a, so minus 3 over 2. Now alpha beta would be equal to c over a, so 5 over 2. Okay, we can now use these two to find the values of alpha squared plus beta squared and alpha squared beta squared. This one's a little bit easier, so we're going to do that one first. Alpha squared beta squared is just the same as alpha beta all squared. So we'd have 5 over 2 squared, which would give us 25 over 4. So that's our first value that we need. Our second one's a little bit more complicated, like the last example. Alpha squared plus beta squared is going to be equivalent to alpha plus beta all squared minus 2 alpha beta. So we derived that in our last example. So that's going to be minus 3 over 2 squared minus 2 times 5 over 2. So it's going to give us 9 over 4 minus 5, which is equivalent to minus 11 over 4. So that there is our second value. So we can now put those two values into this equation and then rearrange it to make it a little bit simpler. So we're going to have x squared minus 11 over 4 x plus 25 over 4 equals 0. So this minus minus is going to become a plus, and we're also just going to go through and multiply everything by 4 so that we're getting rid of our fractions. So it's going to give us 4x squared plus 11x plus 25 equals 0. So the roots of this new equation are the squares of the roots of our original equation. All right, our last example asks us to find the roots of the equation 2x cubed minus 7x squared minus 12x plus 45 equals 0, given that two of its roots are equal. So that means that instead of having roots alpha, beta, and gamma, we're going to call them alpha, alpha, and beta because two of them are equal. So now we can go through and find the sum of our roots 1 at a time, 2 at a time, and 3 at a time. So that means that alpha plus beta, so adding all our roots together, would be equal to minus b over a, so minus 7 over 2, so just 7 over 2, which means that 2 alpha plus beta equals 7 over 2. If we do that, the next one, so we'll have alpha plus alpha beta plus alpha beta. That would be c over a, so minus 12 over 2. Simplifying this, we'd have alpha squared plus 2 alpha beta, which would give us minus 6. And our last one, 3 at a time, so we'd have alpha beta, would give us a minus d over a, so minus 45 over 2. And we can just simplify that again, so alpha squared beta is minus 45 over 2. So now we have 3 equations, 1, 2, and 3. We have 3 equations and we have 2 unknowns. Now to solve equations, simultaneous equations with 2 unknowns, we only actually need 2 equations. So for now we're going to ignore this bottom equation. We're going to use equations 1 and 2 and we're going to solve them simultaneously. So from equation 1, we're going to rearrange it to make beta the subject. So we'd have beta equals 7 over 2 minus 2 alpha. Now we're going to sub that into equation 2. So substituting it in here for our beta, so we'd have alpha squared plus 2 alpha outside of 7 over 2 minus 2 alpha equals minus 6. We'll go through and expand that out. So alpha squared plus 7 alpha minus 4 alpha squared equals minus 6. So that's going to give us minus 3 alpha squared plus 7 alpha equals minus 6. I'm going to take it all over one side of the equation and make our coefficient of our leading term positive. So we'd have 3 alpha squared minus 7 alpha minus 6 equals 0. Then we can factorize. So whichever method you want to use, but we'd end up with 3 alpha and plus 2 and minus 3 equals 0, which means we're going to have alpha is equal to minus 2 over 3, or alpha is equal to 3. So there are 2 possible values for alpha. Now we need to find the corresponding values for beta. So we're going to sub this back into this equation up here, and that would give us beta of 29 over 6 for this one. And if we sub alpha equals 3 into here, we'd end up with beta equals minus 5 over 2. So at the moment, it's looking like we have 2 possible solutions, 2 possible values for alpha and beta. But we only know so far that they satisfy equations 1 and 2. We have to be careful that they also satisfy equation 3. So we're going to check each of those in equation 3. So we check this one first. We'd need minus 2 over 3 squared times 29 over 6. If we put that in our calculators, we'll end up with 58 over 27. So that's not minus 45 over 2 that we were going for. So that means that this one here is not a solution because it doesn't satisfy all 3 of those equations. Let's just check this one. So we'd have 3 squared times minus 5 over 2, which would give us minus 45 over 2, which is what we wanted. So our final answer is that alpha equals 3 and beta equals minus 5 over 2. Right, so it's an introduction to the roots and coefficients of polynomial equations.